All right, we are taking a look at topic 7.11, Introduction to Solubility Equilibria Guided Notes. So we are going to take a look at what solubility versus molar solubility is and how we calculate the what's called a KSP for a chemical. So we are defining solubility is defined as the amount of solute that will dissolve to form a saturated solution at a particular pressure and temperature. So we're going to talk more about what saturated means in a minute. But to get us started with things that are familiar, we need to be able to write both a dissolution expression, so when we dissolve something in water, how do we write that, and then how do we write the KSP expression for that. So both of these you'll notice, this one is missing the solid part, but both of these start as solid. So all the time, every time we look at these, if they give you the solid, these are two things that we should be able to automatically write. We have done this part before, where we take a chemical and we break it into the ions. That's why we practice pages of that in Unit 2. So if we break this into the ions, you have calcium and you have hydroxide. You have two hydroxides, so we bring that to the front. We write their charges. Calcium is in group 2, so it's 2+, meaning hydroxide has to be negative because there are two of those, add up to 0. And these are dissolved in water, so we're writing aqueous. We do not write the water, okay? Even though it is saying we are dissolving in water, we don't write the water. We just show the solid and then the aqueous form. So the aqueous part kind of takes the place of writing water. We can do the same thing for iron. Iron 2+, aqueous. Again, it has two hydroxides, so that's why iron has to be a 2+ charge. We get our aqueous. So we can write a reaction. I call it a reaction kind of in quotes because they're not really reacting, we're just separating the ions. Now to write a KSP expression, just like we've written all of our expressions, SP stands for solubility product. Okay, and we'll talk about why it's product in a second. So when we do any of our K expressions, it's always products over reactants. So my products here, I've got calcium ion. Write the charges. It is part of the chemical. If you write Ca versus Ca2+, those are two different things. One is a shiny silver metal and one is ions that are white and chalky looking. Now there are two hydroxides, so we're going to square that one. Our reactant is a solid. We do not include pure solids or liquids. So there is no denominator. You can imagine that it's over 1. We don't write the over 1 though, because it will just add more things we don't really need. We can do the same thing for the other one. We've got iron 2+, and we've got hydroxide squared. Okay? So those are our solubility products. Notice that it only includes the products of this reaction. And a product is when we multiply things. So that's a couple reasons why we call it a solubility product. Now, just for comparison's sake, I'm going to give you the values. For calcium hydroxide, it's 5.5 times 10 to the -6. I ran out of space here. And for iron hydroxide, it's 8.0 times 10 to the -18th. Just for comparison purposes. All right, and this says, why do solubility equilibrium expressions? So why do these not have a denominator? Because reactants are solid. All right, we don't include those solids. Okay, continuing. When a solution is in equilibrium, the concentration of the dissolved solution remains constant. So when we dissolve something, we take the solid, we put it in water, it dissolves. The concentration of our dissolved solution remains constant. True. That's like saying your molarity is constant at equilibrium. That is a true statement. Once it's dissolved and we establish our equilibrium, it's going to stay dissolved. Now you'll notice that these do have double arrows. Not all of our chemical is going to dissolve. We can see that based on our values here. When a solution is in equilibrium, the solid salt is always completely dissolved. False. Okay, we will not always dissolve everything. So I could take calcium hydroxide, I could take 10 grams of it and throw it in my water, a liter of water, and maybe all of it will dissolve, maybe not. But we're going to base how much dissolves is based on this KSP value. Okay, that's going to help us figure out how much dissolves. Okay, so our molarity is based on our moles per liter for our solution, but we're going to also look at what's called our molar solubility, how much actually dissolves, not how much we put in the container. Okay, so this table kind of gives us some comparisons, okay, to look at with these two chemicals. So which salt is more soluble? How do we know? So we're going to look at our KSP value. The larger our KSP value, the more soluble our substance is. Well, why is that? If we have a larger value here, that means we're going to get bigger values here. If we have bigger values here, that means more of it is dissolving and changing into that aqueous state. So in this case, when we look at our exponents, remember that a smaller negative exponent is a larger value overall, right? This is like this is the same as 0.00000055. This one would need 17 zeros before we get to our 8, right? Much smaller number. So this one is bigger, so calcium hydroxide is more soluble because its KSP value is larger, which means there is more product in solution, so it must be more soluble. We're getting a larger amount of ions in solution. So which salt most likely has stronger intermolecular forces with the solvent? Explain how you know. Well, our intermolecular forces, if we can pick an ion, so I'm just going to pick that first one, calcium. We've got an ion, we've got water that it's hanging out with, our Mickey Mouse molecule there. And the positive ion of calcium attracts to the negative part, the oxygen on the water, and we form an ion dipole force. So the stronger the attraction between those, the more of these ions we're going to get, the more it's going to dissolve. So since calcium hydroxide has more of it dissolved, it has to have stronger interactions or stronger IMFs. Okay, so calcium hydroxide has stronger interactions with the solvent. We know this because more of the salt is being dissolved into solution. All right, you have 2 flasks at equilibrium, one of aqueous calcium hydroxide and one of iron 2 hydroxide. So they're at equilibrium, they've achieved these KSP values. Which flask has a higher concentration of ions? Okay, so who has more ions? Who has more of these hanging out? Well, again, calcium hydroxide has a higher concentration of ions because it is more soluble. More will be dissolved. Okay, more soluble because it has that larger KSP, right? We're favoring that, not favoring the products. The products are favored more in this one than they are in this one. All right, you allow the solvent to evaporate from your 2 flasks, increasing the concentration of ions in each. So when we take away some of the water, we have a higher concentration overall. Which salt would precipitate first? Okay, so as we start to take water away, we're going to start having some of these ions not be able to dissolve anymore. Okay, and the reason is because they're not able to. They don't have as big of a KSP value. So iron hydroxide will precipitate or turn into a solid first because it has a lower KSP, meaning it's less soluble, fewer ions can be held in solution. So when we dissolve these, the water can only hold so many little ions. And if we take away that water, those ions can't be held anymore. So they got to come out. They got to start forming solid. So let's take a better look at this saturated idea. So what's in the beaker? When something dissolves to create a saturated solution, there are 3 points we can look at. So first, we have a beaker, we have our solid, and we start adding it to the beaker, okay? The solid is going to start to dissolve. So this is below our saturation point, right? We just added a little bit. So below our saturation point, we can have more dissolve. So we got our little solid at the bottom, our little particles, and we can see in our picture here, those solid particles, the ones that kind of are just outlined there, are becoming dissolved. Okay, so we've got arrows going out. Okay, that is dissolving. And we can see there's one here where the arrow goes in. That's where we are forming the solid, so we're precipitating. Okay. So we have more arrows going out than we do coming in. So overall, we're dissolving. We're getting that chemical to all break apart. If we only have a little bit, we're below saturation, our solution is going to be clear. Okay. Now it could be clear and have a blue tint. It could be clear and have a green tint to it, right? A color. But think about like red food coloring in water. You can still see through the water. It just has a color to it. So it's clear. It's not cloudy, right? There's no solid. No solid, right? It's all being broken up. Okay. So when we reach our equilibrium point here, where there's well, actually, we wouldn't reach an equilibrium. We'd only go one direction. All right, when we're right at the saturation point, we have a saturated solution. No more can dissolve, but no precipitate forms. So we have an equal direction where we have things going out and coming in, dissolving and solidifying. So since those are at the same rate, right, once we solidify one, it's going to dissolve again. Creating an equilibrium. This is where our KSP is measured, all right? So when we can get everything to dissolve there. So we have our rates of our dissolving and our solidifying are equal. So we get equilibrium. Again, we will have a clear solution. No solid. So it's a little hard to tell the difference between these two if we just look at our solutions. We won't know something is saturated until we add just a teeny tiny bit more of the solid and then it doesn't dissolve. And that's when we reach the above saturation point. No more can dissolve and excess is as a precipitate, okay? So we're getting some of it to stay in that solid form. At that point, we have more going in to precipitate than we do to dissolving. Okay. Now, we can still have a KSP here, but we're going to have some solid at the bottom. All right. We can still reach an equilibrium, but we're going to have solid at the bottom. All right. So just to give you a visual there for those. Now, we can do some calculating dealing with KSP, of course. So this one, for any of these questions, two things you can always do, no matter what information they give you, is you can write a dissolution equation and you can write an equilibrium expression, or KSP expression, okay? They won't always say to write these, but they're very helpful because they give you a starting place. So I encourage it strongly. Now this one says to write the dissolution equation for the dissolution of AgI, solid. So we're just going to break it apart into its two ions as aqueous. Now we have to put charges. If you do not put charges, it's incorrect and you haven't written ions. So I know iodine is in group 7, so it's negative, which means silver has to be positive since there's one of each. Now, the next thing we can always write is our KSP expression. I've got silver, and I've got iodine, and there's no denominator because our reactant is a solid. Now, this says you have a saturated solution of silver iodide in a 1 liter beaker. Calculate the concentration of iodine in solution if silver is 8.8 times 10 to the negative 7th. We don't know iodine. At this particular temperature, KSP is 8.5 times 10 to the negative 17th. So if I want to solve for iodine, I'm going to divide by my 8.8 times 10 to the negative 7th on both sides so I can isolate my iodine. So the concentration of I minus would equal, let's see, 8.5 times 10 to the negative 17 divided by 8.8 times 10 to the negative 7th, and I get 2 sig figs, so 9.7 times 10 to the negative 11th. Now it is asking for a concentration, so that is a molarity. Okay, so given the concentration of one, I can find the concentration of the other if I have my KSP. So that means that's the amount of ions in this particular container. All right, now if we want to find the KSP of a chemical, it says write the dissolution equation for barium chloride. So we always start as solid. We're breaking it into its ions. There's 2 chlorine, so I'm going to put 2 in front. They're both going to be aqueous. And I'm going to add my charges. Chlorine is negative because it's in group 7. I have 2 of those, so I have to have a 2 plus here. Also, barium is in group 2. I can write my KSP expression every time. So Ba2 plus, and I got chlorine, and there are 2 of them, so I'm squaring it. If the concentration of the saturated solution is 0.75 molar, determine the concentration of each ion in the saturated solution. Calculate KSP. So I have the concentration of the whole solution, okay, 0.75 molar. I want the concentration of the other 2 ions, okay? So we want to basically do a mole ratio. If this is 0.75 molar for the whole thing, and it's a 1-to-1 ratio with barium, then barium is 0.75 molar. If it's a 1-to-2 ratio with chlorine, chlorine is going to be twice as much. So 0.75 times 2 gives me 1.5. I'm going to plug those in and solve for my KSP. 0.75 times 1.5 squared gives me 1. Let's see, we got 2 sig figs, so 1.7. All right. And K values have no units, so we're good on that one. All right, next, we want to find the molar solubility. All right, the bell is about to ring, so I'm going to have to pause the video here. I'm going to go ahead and record the next part later, and I'll post that as a separate video for you guys.